right? And you can see over here at the top, okay, at the top, you have compression. Because the circumference is smaller, at the bottom is stretching, it is tensile, right? But this can be easily solved by you looking at the moment vector. So the head of the moment vector is compression. The tail end of the moment vector is in tensile. Okay, so I want you to at least visualize what is going on. This is only true if your moment vector, the direction you assume is correct. So how do we know it's correct? We do static analysis. Okay, we do static analysis. So the next thing we're going to do is we are going to do static analysis. To determine the direction of the moment vector. Okay, so we are going to do summation about moment, about the y-axis, and we are going to take the moment at point H. Okay, so we're going to take the moment at point H. Okay, so this means we're going to analyze the moment about the y-axis and from point H. Okay, so using static analysis means the whole thing must be equal to what? 0. Okay, so we are going to take moment at point H. Okay, so the first 600 that I'm highlighting in yellow now is going into a clockwise direction. So minus 600 multiply a distance of, if you look at the small image over there, is 6 plus 8. Right, and then the next 600 is going to rotate in a anti-clockwise direction plus by 600 multiplied by a distance of 8, right? Because the blue highlighted 600 to point element H is only 8 inches. Okay, and then the moment, because it's the moment about the moment over here, right, is going into a anti-clockwise direction plus by moment H, point H is equal to 0. Okay, so when you calculate moment at H, at point H, this will be equal to 14 minus 8 is equal to 3,600 positive pound inch. Okay, so when it's positive means the direction is correct. Okay, so it's going in the anti. So positive means the assumed direction is valid. Okay, if it's negative, change the direction.
Hey, Eugene, are you able to scroll to the left a little bit?
Okay.
Thanks, man.
Okay, sorry about that. Okay. So now we know that is 3,600. Okay. And what you see down there is element, the 3,600, right, is going to induce a compression. Okay, because of the way the moment vector has been drawn, right? You can see down here is going to be in compression. Okay, So now we try to find what is the stress. Okay. So the stress, so we are now finding the stress in the x direction. So stress in the x direction is equal to moment about y, right? Or I'll just say, yeah, moment about y. And make sure I won't make this too difficult for you. Divide by I, multiply by y. Okay. So what does this mean? Okay, so I'll define for you. By the way, this formula, because our exam is online, okay, you can refer to all this. Our exam will be online, you know that, right? Okay. So what does this mean? So my, or stress x, is the stress in the x component. My is moment about the y-axis, right? I is the second moment of area. So I give you the formula for I is equal to pi over 4 multiplied by the radius power of 4. Okay. And y over here is the furthest, or I'll put down here the radius of the shaft. Okay. So now we can calculate our stress x, and we know that it's going to go to compression due to the moment vector. Okay. So stress x is equal to minus 3600. The shaft is 1.25 diameter. We divide by 2. Okay. Then we divide by I, which is equal to pi over 4, multiply by 1.25, divide by 2 power of 4. Okay. So this will be 3600 divided by 1.25 divided by 2 power 3 divided by shift pi times 4 is equal to 18.775 minus 18.775 times by 10 to the power 3 psi. Okay. So when we go back to our element, we have good news. Okay, we have good news. We now know that stress x is equal to minus 18.775 times 10 to the power 3 psi. Okay, we found our value. Okay. And then for the next one, we look at static analysis. Summation about forces in the y direction. Is it y? No. Summation of forces in the z direction is equal to 0. Okay. So if we look at our free body diagram again, okay, over here I'm going to have a vertical force go up, okay, and this is our VH. Okay, that's my VH. So we are doing static analysis again. Okay, summation of forces is that z direction is equal to 0. So you have 600 minus by 600, okay, plus by VH. So the shear force at BH is equal to 0. Okay. So as I said, this is my favorite question. It will always be 0 because all of you have not taken structure analysis yet. You will not know how to manage this data if it's not equal to 0. Okay. So now let me write something out for you regarding this. Over here, the I is for solid shaft. If for hollow shaft, I is equal to pi over 4, okay, R naught to power 4 minus by R internal power 4. This is for hollow shaft, where R naught is the outer radius, and Ri is the inner radius. Okay. So for this problem, it's a solid shaft, okay, and we can see from here, right? Over here, we can see that, or from this diagram over here, right? We can see that stress Y, there's no forces coming in the Y direction, so stress Y is equal to 0. Okay, there's no bending in that direction or whatsoever. Okay, so now the next thing that we're going to look at is we're going to calculate shearing stress. So we have our stress X. Next, we want to find out our shearing stress. Now, shearing stress is very critical. Okay, stress X is inwards. You're right. Okay, is compression. Okay, Han Chong. Right. So now the next thing is our shearing stress. Now, shearing stress, as I said, is critical, especially for carbon fiber. For solid material, does not matter. For carbon fiber, it's ever so critical. Okay, and I'll explain to you why. So now let's focus on shearing stress. Okay, so I'm going to take my figure again. That's why for this topic, I cannot use the light board. I have to use the notebook, okay, or OneNote. Next week, we'll go back to the light board again, and you get to hear the squeaky pen. Okay, so what we are going to do now is we are going to look in a direction where this is the X and this is the Y. Okay. And I'm going to draw to you the we're going to look at the shearing stress. Okay, so what we're trying to do is to determine the shearing stress okay, induced by the torque. So the torque over here is in the X direction and it's at 2,500 pound-inch. Okay, 2,500 pound-inch. So the formula that we're going to apply is the shear stress. I think those of you who have mechanical engineering, you guys who have finished this, which is TR over J. Have you guys finished learning torsion, yes or no? Anyone?
We just finished that like this week, I think.
Yeah. So you all know. So where tau is the shearing stress. T is the torque. R is the radius of the shaft. J is the polar second moment of area. And J just to make it short, and I'm not going to explain why. So J